Good evening, everyone, and welcome to this evening's event. I'm Roxanne Martin, and I head up the Eagle Lab Industry Programming on Agritech. And we're joined here tonight by two fantastic speakers who will be going through the benefits of soil health, soil monitoring, and carbon sequestration. So we hope that you'll find the content interesting. Before I hand over to our two speakers, I'm just going to quickly run through with you, for those of you who don't know who Eagle Labs are, what the Agritech industry programming is about within Eagle Labs, and also why we've chosen soil health as tonight's topic for the event. So without further ado, Eagle Labs, we are a network of business incubators. We have 25 live sites at the moment across the country. That makes us the UK's largest network of business incubators across the UK. We're part of Barclays. We have three areas of expertise within Eagle Labs to support our tech entrepreneurs to grow at an exponential rate. So first, number one is all around accelerating UK business. Now, what do we mean by that? We provide connections to for startup businesses through our network, vast networks within our individual locations across the UK. We provide mentorship through our partnerships through Judge Business School and Codebase. We provide access to our investor network, and then we also provide access to potential target markets as well for our startups. So we hopefully can help support our startups to hopefully outgrow us and move on to pastures new, and that's very much the business model that we operate. So that's number one. Number two is all around collaborative innovation. Now, what we mean by that is how do we connect our startup community with our larger corporates that we support within our Barclays network. So we're providing our startups access to their target market, but we're also supporting our larger corporate businesses to act and behave entrepreneurially so that they're not left behind within Industry 4.0. And that brings me on to my last pillar, which is very much focused on Industry 4.0. So what we mean by that is all around the demystification of technology and making technology relevant and accessible for everyone. And an example of that is our extensive events program, and this event this evening forms part of that program. So onto agritech as a specific industry. So our vision is simple. We want to become the number one bank for driving positive innovation in agriculture, and we want to do that through supporting the UK supply chain to become the most sustainable ecosystem in the world. And how do we plan on achieving that? Is through the demystification of technology and encouraging collaboration across the whole food supply chain from field to fork. We simply want to be able to feed the world without wrecking the planet. So Agriculture 4.0. We see very much Agriculture 4.0 as a tool to support the farmer rather than to replace the farmer. We don't see that robots are going to be coming in and taking over the farming industry, but it will help enable our farmers to make better decisions over the land of which they look after. We think that Agriculture 4.0 will help farmers become more efficient, improve productivity, save time, and also arguably probably one of the most important points is to make the industry a more sustainable industry to feed generations to come. Which brings me on to a little bit more around tonight's topic, which is around why soil health. So healthy soil is fundamental to Britain's farming system and producing the food that we eat. So it provides the means for plants to grow, and it helps to create the oxygen that we breathe and clean the water that we drink. So I think you would agree with me that it's a pretty important topic for us to be discussing this evening. Soil can also help increase our resilience to climate change, and that's done through storing carbon, locking in greenhouse gases that would otherwise be released into the atmosphere, and also therefore helps to prevent flooding. So some facts for you. So there's more than 700 different types of soil in the UK. The more farmers know about the soils that they have on their farm, the better decisions that they'll be able to make to help improve the health of those soils. And just another statistic taken from a 2018 government survey into English farming practices showed that 74% of farmers knew the soil type for each of their fields on their farm, and 35% actively tracked organic matter contained within those soils. So we've actually got a quarter of our farming industry out there that don't know the type of soil that they're farming on. and a whopping 65% that aren't actually tracking the matter within those soils as well. So it's a huge opportunity for soil health and the soil health market. So what are we looking at? So new technologies and techniques that are being developed to help farmers look after their soils. So we can take that 75% up to 100%, hopefully. The outcomes of this would be around reducing soil compaction, reducing the amount that soil is disturbed, and ultimately improving productivity and sustainability. Soil condition monitoring sensors, and these allow farmers to collect data about rainfall, temperature, and other metrics over time to track trends and predict irrigation needs. Devices capable of measuring microbial activity in the soil. And another example of technology in this field is IoT-enabled sensors, which take very little time to set up, and they have a long battery life, and this leads to less maintenance costs as well. So what are the benefits of this new technology? So a statistic from IBM estimates that IoT will enable farmers to increase food production by a whopping 70% by the year 2050. Now, if we think about the statistic around, we probably need to produce between 70 to 100% more food by 2050, depending on where you look and what reports you read. That means that we're going to potentially soil health will have a huge positive impact on food production and the need to produce more food to support the ever-growing population by 2050. It reckons that IoT could save up to 50 billion gallons of water annually, as sensors can help farmers optimize water usage, and better optimization of crop management will have a transformative effect on agriculture in the following years. So just before I hand over to our first speaker, I just need to read out this disclaimer for you, which is a regulatory requirement. So please do bear with, and I will hand you over to our first speaker. But we've asked both Professor Guy Kirk and Phil Jarvis to join us today to provide some tips and tricks on good soil health and the benefit it brings. These topics discussed are an overview and options for you to think about and to help with your own independent research and business decisions, and they're not intended as recommendations or advice. Remember as well that your business has its own individual circumstances. The statements and views expressed may not be applicable or suitable to your business. So without further ado, I'm going to hand over to our first speaker, Phil Jarvis. Now, Phil Jarvis is part of the Game and Wildlife Conservation Trust. So Phil, over to you. Okay,
good evening. My name's Phil Jarvis. I'm from the Allerton project, the Game and Wildlife Conservation Trust Allerton project, based on a 320 hectare farm in Leicestershire. And I'm going to talk to you about our experiences at our farm in Leicestershire and try and put into context some of the things on net zero, greenhouse gas, but really practical things that farmers can do and the things that we've been doing here with our research colleagues and looking at why soil health is so important. So the Allerton project has three aims, really. First one is to look at productive farming, really key in our food production. Secondly is to look at the environment, landscape, and wildlife that go hand in hand with that landscape. And the third thing is, with our findings and our research, is to look at how we can disseminate them to a wider audience. So let's have a little look. But before we start on soil health, there are a few caveats that I'd like to firstly mention. And these are my opening caveats. Soil has a number of limitations. So your soil may be limited by what texture it is. It's sand, it's silt, and it's clay content. And sometimes you can't change that. Yes, you can improve it. You can alter it slightly. But if you're on a sandy soil, you're unlikely to be able to make it a clay soil. And if you're on a silty soil, you're unlikely probably to go either way or the other. There are some manipulations you can make. However, drainage as well. Drainage is an issue. Sometimes underlying drainage, clay soils tend to be waterlogged, sand soils, much freer draining. Yes, heavy land farmers can put artificial drainage in, but there are some things which naturally occur and limit what happens to your soil. Slope and aspects. If you farm on an area that's very flat, you'll have different sorts of problems to someone who's farming on very hillside land, north facing and sloping, and you'll have individual problems or issues and challenges with your soil. The underlying nutrient status as well. So with your soil, you'll find things like your phosphate levels or your calcium levels or your organic matter levels will provide different status to your soil. So they are things you'll have to be aware of. And also what appropriate crop choice you're going to put on that soil. And that's very key as well. Some things like growing on certain things, but not on others. The other thing is weather, and we're in the middle of some strange weather patterns, and obviously climate is a big issue. But we have to really look at what wet weather can do to your soils and how you can make your soils much more resilient. Also, how do we value soil health? Because whatever happens in the financial arena of what a produce is worth or what environmental safeguarding is worth, that has a huge influence on what happens to our soil. And the final one is that we can have lots of aspirations, but sometimes we have to be realistic about what we can achieve. So without more ado, we'll start on the first part of it. So I'm going to look at soil production systems, and on the left here you can see that we've got a crop of wheat, and on the right here we've got a traditional hay meadow on our farm, and behind it a woodland as well. And at each end of those spectrums, the soil supports those production systems. So what you want to get out of it, whether it be food on the left, or maybe there's food here because this will be made into some hay, but there'll be a lot of other things that use either the trees in the background and the flowering plants in the foreground. So what are we using our soil for? At the Allerton project, we've been involved for over 25 years on looking at conservation agriculture, the balance of soil and water, and it's all in one of our documents called Fields for the Future, a blueprint for farming and wildlife and the environment. But much of our work is concentrated on soil and water. So I'm going to talk about the relevant and practical solutions for successful improvement of soil health and conservation agriculture to regenerative and restorative systems. There's been a lot of talk of conservation agriculture, and there's a lot of talk about regenerative systems. So what are they? Firstly, conservation agriculture really is looking at reduced cultivations, wider rotations, continuous or as much as you can soil cover. If you add to that grass and livestock, it may well just be grass, which you use for fertility, or you may well have livestock grazing that grass. That starts to get us into regenerative and restorative systems. One key ingredient missing here, of course, is that there is a mindset that has to be done to make these systems work. They are sometimes much more difficult to comprehend, and sometimes we need to create incentives which pursue those new avenues of conservation and regenerative agriculture. So looking at the first one of them, and reduced cultivations, and why is that important for soil health? Well, you can imagine a tractor like this, which might weigh anywhere from, tractors on farms anywhere from 8 to 15 tons. The lighter your tractor, the better the tire pressure. The least amount of cultivations puts less pressure on your soil, and therefore means there's much more development for root growth, water movement, air into soil, which are all the things that plants need. So it's really a cornerstone of our farming system. A wide rotation. Now, this is our rotation for this year, and it would be fair to say that we have a predominance of spring crops. We're traditionally heavy land cropping because we're clay soils, but the weather too wet over the winter period has meant we've been forced down a route of growing lots of spring crops. So spring oats, spring barley, spring beans, and spring wheat. But a wide rotation is good for soil. It's good. You have less diseases, less pests. You can use your rotation to fertility build. You can help to enhance some of the natural biodiversity in the soil. And not only within the rotation, but perhaps within some of those crops, we may well even talk about a wider biodiversity of some of those catch crops, different varieties, different things grown during the year. So that's the second pillar. The third one is soil cover. And this is one probably at Allerton we could probably do more on this. We've got soil cover here where we actually, this is a cover crop grown after harvest. We've chopped the straw, left it on the surface, grown a cover crop, and then we'll either graze it off or we might spray it off, and then we'll plant a spring crop in there. And that's really like a coat of soil armor. So this is stopping the impact of heavy rain. It's hitting the cover crop first and slowly filtering into the soil rather than hitting a dense compact surface and running off. The fourth bit is livestock and grass. These are some of my Leicester longwools on the left-hand side. They're a rare breed. They're grazing that traditional hay meadow supported by an agri-environment scheme. once again bringing diversity and genetic diversity into our our species and varieties. We rely on very few species of plants and animals, and actually within there we do need to keep some genetic variation. And on the right hand side is grassland. Now this is a herbal ley. It has plantains, red clover, white clover, chicory, salad bonnet, and its whole purpose is to fertility build, structure the soil, and really make a good start when I return it into my rotation. And you'll see in the background we're quite a rolling landscape in High Leicestershire, so we do have issues with runoff. But most of what I'm going to talk about now about monitoring will be around our conservation agriculture project, which we've been doing with our partners Syngenta. And if I look at this picture here, this is a drone shot from last year, where we've got on the right hand side a plough plot. In the middle there's a section where it's been minimum tillage, which basically means it hasn't been turned over like the plough system. It's been just minimally cultivated, maybe 1 or 2 passes, not turning the soil over. And the green strip towards the left there, the greener strip, is where we've drilled basically straight into last year's crop. And then we've looked at what that means for our soil and how we measure them. So the project looks a little bit like it. There's 5 fields here that you can see. And if you look at those plots again, this is a different field, one of the different 5. You can see plough for the plough plot, min till and light till. And you can see this normalized difference vegetation index is NDVI, and that just reflects what's growing. So the green shows you which bit is growing the most crop, and that's one way that we're monitoring plant growth. But all through time and all through on this project as well, is mankind has been monitoring and manipulating the soil. So what sort of monitoring can we do? So we've got physical, chemical and biological monitoring, and we'll just have a look at some of those. So physical monitoring, for most people on a basic level, what is your soil type? Where does it sit? For example, in the clay content of this graph, soils that have very little clay content, so on hard soils here, 30% is high. If you've got, and you'd think, oh, well, that, there must be 60, 70, 70% of something else. Well, clay has a really big effect on your soil. So you don't need much clay in a soil to make it show characteristics of stick. Think of pottery, think of things that stick together. That's your clay soils. So basically monitoring, when you're sending your soil samples off, seeing where your soils lie. How much silt do they have in them? How much sand do they have in them? How much clay? And that shows you the appropriateness of what you can crop on your fields. Physical monitoring as well. So there's nothing on the left-hand side there. Is a spade, which is dug a spit of soil, and that's a very easy, and you can see just from a simple exercise like that, you can see those horizontal lines where you've got some slight compaction layers, and that's an indicator straight away about some of the issues you have. In the middle there is a penetrometer, and this is a digital one. You may well be familiar with one that has a circular scale on it with a traffic light system on, and this is just measuring the pressure of the soil as you go down through. And of course the graph on the right there shows the force that it takes, that the soil is there. It's measured in kilopascals, and that's what the roots have to penetrate. So of course you're looking to keep everything as far to the 0 scale as possible, because that makes it easier for roots to go. And of course some of what we're experiencing at the moment is very dry soils, where this structure of soil gets very much tighter and roots can't penetrate, and therefore crops are a bit stunted. So of course, what's this telling us as farmers? Whether it be with a spade or whether it be with monitoring with digital appliances, or whether we're doing bulk density and drying all the water out and looking how dense our soils is. But it's basically telling us, how should we set our machinery up? Do we need to use a machine like this? Do we need to set a tine in there? Do we need to loosen our soil? Or is it loose enough for us to use less diesel, less passes? And of course, the less passes we do, the less we have to compaction appears in our soil. So the next thing I'd talk about monitoring is a VESS score. Now this chart on the left here is basically taking that spit of soil and looking at its breakup, looking does it break down into friable constituent parts, so you give it a 1 score, or with the very bottom of that scale where you've got a very compact solid clay where you'd give it a 5. And the graph on the right really is looking at those 3 cultivation systems. So the red is looking at a plough and a min-till and light till, and looking at how those how that visual assessment is in each of those sorts. So, you know, all those scales are under 3, so they're relatively good, but the far lighter yellow one on the right hand is beginning to show some benefits as we're coming forward from 2017 across to 2019, and we're looking for that graph to show us lower scores. It's very easily done. It's an assessment you can do in the field and see where your problem is. Do you need to go and cultivate? Can you monitor it on the ground? Very simply. This is more traditional, so this is some monitoring of the chemicals that are going on in our soils, so our phosphate, our magnesium, our nitrates, and looking at what their status is. And by monitoring this, you can see, do I need to add anything to my soil? Are my levels normal? Or do I need to manipulate the sorts of things that go on to try and enhance the amount of crop I grow? We're going to be also talking about greenhouse gases, and this graph here, so some of the monitoring we do on the Allerton project here, on our project, is looking at the green bar is in our ploughing field. So this is the one, the conventional tillage, turning the soil over, maybe cultivating it 2 or 3 times. And then the other two, the orange and the grey graph bars, are just showing you minimum tillage and light tillage. And really, the issue here is around the difference between the green and the grey and the orange bars. That difference is almost 40%. So that's a 40% reduction in greenhouse gases because we've got less gases going up into the atmosphere from our cultivation practice. So keeping an eye on that. Probably not the sort of thing that a lot of farmers could do, but it's the sort of thing that can get modelled across a lot of cultivation systems if we start to be monitoring what we need to do around net zero. Monitoring organic matter. Now, there will be lots of debates, and we can talk about what sort of organic matter is. Is it soil carbon? And these are some of the organic matters from our plough, min-till, and light till systems. And really, for a heavy land farm, these are surprisingly good for us. But I think, you know, one of the things I would recommend to government, to farmers, and those in the industry is that every soil sample we send in, we should be looking at our organic matter, capturing carbon. Much more exchange sites for nutrients, to exchange drainage, a whole host. It's a food source for lots of other things. It's really important. And of course, there'll be lots of areas where increasing that organic matter is fantastic for net zero, taking carbon dioxide out of the atmosphere and putting it into your soil. So this is bear with me with this one. I'll try and explain it as simply as possible. It's all very well having high organic matter. And we've talked about a little bit about greenhouse gases, but let's just look at this graph here on the left-hand side, which is a green T and red T. Each bar represents each, and it's the decomposition rate over a 60-day period. And you'll see that 74% in plot 1 has disintegrated and completely disappeared. And the red T is a more woody T, so it doesn't break down as much. And you'll see in those 3 graphs there, the last graph there is the one that's had a very sustainable system. And you think, well, hold on a minute, the green area hasn't disintegrated as much, and the red T is integrated a bit more. So surely that's not very good disintegration. There's not much soil biological activity going on. But if you look on the graph on the right there, it's really saying, and if you look at the difference there between those two with this tea bag test, it's saying that if that green tea doesn't break down so much, a lot of that organic matter is still in the soil, okay? And it means that that soil, not only is it working and it's breaking down, but it's not releasing a lot of that decomposition tea up into the atmosphere. So what we're trying to do is that very active soil that keeps that organic matter in the soil, doesn't turn it to a greenhouse gas, gives us all the benefits of growing a crop, drainage, cleaner water, and good root structure. So my next bit is about biological monitoring and earthworms, and these are what I call our underground engineers. You know, they really are a fantastic help to us. You know, they can construct drainage channels, introduce more air into the soil which roots depend on, and in that solution of water and air is the mixture where this cation exchange goes on with nutrients entering the roots. So they really are a farmer's friend. And the graph here just shows on the left-hand side is counting earthworms under conventional system, min-till system, is looking at year 1, 2018. And on the right-hand side, same experiment, but in a very dry year. And you can see the massive effect that weather has on counting earthworms. So, and of course, for farmers, a lot of farmers can just simply go and count. So this was Jackie Stroud from Rothamsted, who was looking at just counting soils out of a spit of soil very simply on a piece of paper and trying to get some idea of where your soil and where your earthworm status is. And as I come to the end a little bit, is to look at the financial performance, because as we monitor soil, we have to look at whether or not our soil performance, our financial performance stacks up. So here, once again, the three systems: the red is the plough, the orange is the min-till, and the yellow is the light till. And you'll see the second load of graphs are the margin after cultivation. So this is where we've got cheaper cultivations in the yellow bar, because we've actually not done as much cultivation, so there's not as much cost. And then if we look on the far right-hand side, we look at what happens then if actually we haven't got as much machinery on the farm. So our fixed costs are much less. So we have maybe one less tractor, one less cultivator, and over rotation, we begin to see that this light till, less intervention approach makes financial sense, as well as hopefully making sure that our soil structure and all the other things, prosper. And that is a real key element there, this business about machinery saving. So some closing remarks. Soil is a complex ecosystem. We could have gone into things like antagonisms around diseases like take-all, and how we can look at biological health and how we can make additions with biostimulants, soil webs, mycorrhiza, trace elements, all those interactions, and all which, as we go forward, will have much more complex and interesting monitoring systems that will become part and parcel of farmers' daily monitoring. It'll also, soil provides a medium which on much of our food and biodiversity depends. So it's really key that you have to monitor it to manage it. And if we want to know about production systems, greenhouse gases, and looking after the environment, having a starting point of what it is, where's our baseline, where are we heading to, is crucial. And my final point would really be to say that improving soil health relies on the right decision, the right time, and the right place. So even with a lot of scientific expertise, a lot of measuring, a lot of monitoring, there is a certain expertise that the farmer will have to say about. And sometimes this can be a few hours difference, a few days, or a few weeks about getting something right and looking after soil health. So there we are. I hope that's left you with some ideas, some thoughts, and I look forward to some of your questions. I'll hand you back to the studio.
So thank you, Phil, for that presentation. That was definitely really interesting. Some really interesting ways to monitor and improve soil health. So thank you for that. Right, so next up we have Professor Guy Kirk from Cranfield University. Now Guy is going to be going through the potential for carbon sequestration in UK soils. So without further ado, I will hand over to Guy.
Thanks very much, Roxanne, and good evening, everyone. Well, I'm going to talk about the national scale. Phil's talked about the field scale. And I'll start by giving you the punchlines, which are really how important it is to think about the system as a whole, as with most things. Carbon sequestration is only one of the functions required of soils. There are many others. Excuse me. So it's important to think about the problem in the round, not just one individual aspect. So that's one. And the second punchline is monitor, 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 as Phil was saying. Like the virus, it's key to be able to measure the consequences of any interventions at the appropriate scale. So those are my two themes. I hope will be apparent as I go through. So we're quite well served in this country with soil data, including information about changes over time. Cranfield, where I work, is the repository of the national soil datasets. as part of our heritage of the National Soil Survey of England and Wales. So much of what I'm going to say is exploiting that data and various applications we can make of it. Well, firstly, by way of background, something on the global picture of soil carbon. This slide shows global carbon stocks, so the amounts held in the ocean and in the land surface meaning soils and plants, and the annual flows between these different stocks, and how it's currently being perturbed by inputs from fossil fuel use. So what it shows is there's far more carbon in the ocean. What's at depth only equilibrates very slowly with the surface. The small amount on the land surface is actually a larger part of the annual flux into the atmosphere. And there's a flux in both directions because plants fix carbon out of the atmosphere, CO2, when they grow. And it's returned to the atmosphere as plants decompose in soil. So all things being equal, that's in balance, but currently it's being perturbed by a small input from fossil fuel burning. It's small relative to those fluxes, but it's enough to be upsetting the system. And the question is, how is the system adapting to that, and how will it in the future? Well, at the moment, about half of that flux is being mopped up by the oceans and the atmosphere. So the rise in CO2 in the atmosphere is much smaller than it would be if it wasn't for these two sinks. And for the land surface, that's because with higher CO2 in the air, plants are growing faster, forests are growing faster, and they're actually taking CO2 out of the air. But over time, other things are going to become limiting, so water or nutrients. And that land surface sink, it's predicted, will run out, whereas with warming, the rate of turnover of carbon in the soil will continue to increase. So the current models say at some point this century, the land surface will stop being a sink mopping up the fossil fuel CO2 and become a source. And then there's a feedback loop, more CO2 out of the land, more in the atmosphere, more warming, which is a pretty scary prospect. But the models are all rather shaky. They're not entirely reliable. It's a much more complicated picture than you might think. But that is one possible outcome. And it says how important it is to think about ways of preserving carbon in soils and, if possible, fixing more. Well, this slide shows that there is something like 4 times as much carbon in soils, the top meter of soil around the globe, as there is in all the vegetation, all the atmosphere. And it depends what environment you're in. There's more in the cold, wet parts of the globe, so peat soils in boreal forests. There tends to be more in plants under forests than in the soil, but on balance, there's much more in the soil. And it's turned over slowly. Most of it is in forms that are only very slowly turned over, but it is turned over. And the processes that determine how rapidly it's turned over are shown here. So there's a balance between what's coming in from plants, being immobilized in the soil in various ways, particularly by interaction between the organic matter and mineral particles in the soil, clays, that immobilize it against decomposition by microbes. But the microbes do slowly turn it over, and all things being equal, there's this balance. Immobilization equals mobilization. The amount in the soil is steady. However, that balance is sensitive to perturbations of any sort. One type of perturbation being change in the climate, so this effects of warming, effects of change in moisture, and then of course soil management, and particularly turning over the soil for crops exposes the carbon to decomposition and tends to drive the carbon out of the soil. So this balance is very sensitive to all those variables. So what could be done to sequester carbon in the soil? Is it possible to increase the amount of carbon sequestered? Phil's talked about some of the ways of doing that. But what are the limitations? And much of the rest of the talk will be actually dwelling on some of those limitations and the importance of looking at the system in the round. Okay, well, the first limitation is that a given soil only has a finite potential for sequestering carbon. The earlier slide showed the difference between different systems. So peaty soils, areas with favoring peaty soils have a larger potential than drier areas. So that's one, it's finite. The second is any change must be for good, because if you change the system, you can lose as much carbon as you've sequestered. The third point is that you need to consider the implications for other greenhouse gases, and particularly nitrous oxide and methane, which are two other gases which agriculture has a large part in their net emissions. Changes in the carbon content of the soil can have a large effect on their emissions, either positive or negative. So that needs to be considered. The next point is that it's important to look at the global picture. So there's no use in doing things to sequester carbon in one part of the world if it means adjustment somewhere else to compensate mean there's a net loss. So, for example, later I'm going to talk about the possibilities for sequestering carbon through organic farming. Organic systems tend to be lower yielding and need compensatory production somewhere else. So there's a balance there between the two sides of that equation. And then finally, this point that many current land uses are actually losing carbon. Before we can actually sequester carbon, we need to change systems just to preserve the carbon we've got. Right, well, what about the picture in this country? And what do we know about carbon stocks in the UK and how they're changing at different scales at different times? And what does that mean for possibilities to sequester carbon? Well, as I said, we're quite well off for carbon, for soils data in general in the UK. And one element of that is something called the National Soil Inventory, which was first made in the late 1970s. It took 5 years to complete it. And what the surveyors did was they went out to about 6,000 sites on a grid, every 5 kilometers, 5 kilometers square, everywhere, not just farmland, but natural, supposedly semi-natural at least, land, everywhere across the whole country. And at each site, they dug pits and they sampled the soil and measured its chemistry. And importantly, they archived some of the samples. So it was put in a store and kept, so we were able to go back later and check that there'd be no change in storage. So we had the archived samples, we had the original distribution of soil properties, and then they went back and sampled between 15 and 20 years later, a proportion of sites, not the whole lot, but most of them. And it was possible with the archived samples to check how the repeated sampling worked, how well we could still analyze the original samples and the precision with which the original sites were revisited and so on. So those are caveats about this sort of data, but we were able to quantify the error. Well, what did we find? This shows on the left side the original picture for soil carbon across England and Wales. Brown is high carbon, so the wet upland areas, peaty areas, tend to be dark brown, high carbon content. Pale yellow is low carbon areas, so arable soils, which tend to have much lower carbon content, you can see. Then on the right, it shows the change over time, so the before and after divided by the time. And quite alarmingly, it shows large losses over large parts of the area. Pale colours, pale green, shows no change or indeed gains in some areas. So low carbon areas weren't changing much, and in some cases they were actually gaining carbon. But over large parts of the country, large losses, and particularly with increasing carbon content in the soil, increasing losses. So we're a bit amazed by this. We somewhat expected changes in arable areas. So large parts of the country under grassland were ploughed up, for example, after the last war for crops, and that will have driven carbon out of the soil, and it takes time for that to work through. But we also saw losses in only semi-natural areas, so hardly under management. So we asked, was this already some indication of this climate signature I mentioned earlier, with warming and other changes? Was carbon already being lost from the soil? Well, it turned out that was only a small part, but it was some part. Mostly this was about management changes of various sorts. But some small part, maybe even 10%, was already due to warming during the 1990s. So quite an alarming result, and emphasizing the need to preserve carbon in the soil. Right, so what are some of the prospects for doing that? What management changes might we use to preserve carbon in the soil and, if possible, increase it? Well, Phil has talked about some of those. What I want to talk now about is the effects of organic practices, which is one extreme case for really sequestering carbon in the soil. And a study that field on what would be the consequences of converting all of food production in England and Wales to organic methods. What would be the consequences for carbon in the soil and the net greenhouse gas balance? And just to explain that a bit, one of the main differences between organic systems and non-organic is that inorganic nitrogen sources aren't allowed. So in an organic system, the fertilizer inputs have to be made up from legume leys and possibly inputs from manures. So it means there's a much greater requirement for leys, fallow periods to build nitrogen in the system. And really that necessarily means there's a lower net production. There's a lower yield because over time more of the land has to be fallowed, but also with less inorganic nitrogen, the production in a given year is lower. So lower intensity, lower production. And that means the shortfall has to be made up somewhere else. So what this study did was to put all these inputs in terms of CO2 emissions. So CO2 emissions in producing fertilizers, in legumes, in livestock systems as well as cereal systems and so on. And here are some of the results. This is for crop production. So the consequence of converting all of crop production to organic methods for England and Wales. What it shows is the production in tonnes per year and the area for different crop types. It shows for wheat and for barley. Net production on the organic system is greatly reduced, although similar land areas. So the amount of land required is greatly increased, and that means more production overseas to make up for the shortfall at home. And what does that mean for greenhouse gases? Sorry, this is a bit complicated, but it shows on the left conventional versus organic. The direct emissions are actually not so different. But when you factor in the emissions from all this additional production overseas that's required to make up for the shortfall, the net emissions are much greater with organic. It depends exactly what the land use change was to provide the land for the extra production. But in the extreme case, the emissions are really greatly increased. And that's without allowing for what's called the carbon opportunity cost. So how much carbon might be sequestered if the land was used for not crops, but actually maximizing the amount of sequestration. Well, just to summarize that, the study showed that 100% shift to organic farming would cause major shortfalls. Something like only 60% of the conventional food production could be produced in England and Wales. So all that additional food would have to be produced overseas. And that results in much greater net emissions. Carbon sequestration can only offset a small part of that. So if greenhouse gas emissions are your sole objective, then sequestering carbon in that way would not necessarily be sensible. But of course, increasing carbon content has many other benefits. How do you monitor that? How do you measure it? What's a healthy level of carbon in the soil for different purposes? This slide shows an index of carbon for healthy soil structure. So the amount of carbon required in the soil for good physical structure, which is a requirement for other aspects of soil health. Physical health is required for biological health, chemical health. And it shows that the index we've derived hinges on not just the carbon content, but also the clay content in a given soil. How much carbon is needed also depends on the amount of clay. And therefore we have an index which runs from 0, which is poor, to 1. And this shows how that index looks across England and Wales for grassland systems versus arable systems. And it shows grassland systems on the whole are quite healthy in terms of this index. But arable systems are actually rather poor in general. In terms of physical health, most arable soils don't have enough carbon in them. And that means actually these soils, there's a lot of scope for increasing the carbon content, both from the point of view of producing better structure, but also in terms of sequestering carbon. So that index gives a way of gauging that, a way of monitoring improvements. So, penultimate slide. I mentioned earlier there, so far we've just been talking about organic carbon in the soil, the carbon derived from plants and other organic inputs. There's also inorganic carbon, so carbonates in certain soil types. And there is a possibility of sequestering carbon by increasing the amount of inorganic carbon in the soil in some circumstances. And this is one of the methods that are being discussed for geoengineering the climate. There are various schemes which are to some extent far-fetched, but this is one which may actually have quite a large potential. And the general idea is that on a geological time scale, the main control on CO2 in the atmosphere is this process: weathering of silicate rocks, so igneous rocks, to carbonate rocks, limestone rocks, mopping up CO2. And that process operates on a geological timescale. And it's the main thing that's keeping CO2 balanced in the atmosphere. And the idea of this process is to accelerate that by finely dividing silicate rocks and spreading them on the land. If you finely divide them, you can increase the rate at which that happens. And in a soil, because plants fix carbon out of the air and concentrate it in the soil by decomposition, the concentration of CO2 in the soil air is orders of magnitude greater than in the atmosphere. So we've got a biological system here for trapping the CO2, and if we can fix it in the soil by reacting it with silicates in this reaction as carbonates, potentially there's a large amount of carbon that we fixed in that way. And particularly if we can do it in such a way that it isn't just in the soil surface, it's throughout the depth of the soil. And that requires some clever manipulation of the chemistry in the soil to do that. The models say this may be a possibility. And the amount's quite large. So just for the UK, even replacing lime with silicates, which does a similar thing, it mops up acidity, and you can do that instead of with lime, you can do it with silicate, so you also take out CO2. Rough calculations show that's almost 5% of the net greenhouse gas emissions from UK farming. So that's a huge amount. And if we can do it with depth without disturbing the crops, so not increasing pHs by amounts that become deleterious, then that's quite a serious possibility. And there are sufficient waste silicates around to do that. This is a topic which is under consideration. Okay, so finally, to wrap up, this last slide gives all the various methods that have been considered for land management changes to sequester or reduce greenhouse gas emissions. I'm not going to go into all of them. I just want to make the point that it's important to consider the system as a whole and to look at the various interactions between the two, between any changes. The top two here are changing diets. So there's a lot of discussion about possibilities if we eat less meat. We have a large impact by doing that, but of course there are many other processes that that will affect. Likewise, reducing waste from food is a major contributor to global emissions. Those two are the front runners on this list. Direct carbon sequestration for its own sake is somewhere down the list, but as I've been saying, there are of course other benefits from carbon sequestration, so it's important to look at the system in the round. Right, well that's all I want to say.
Great, thank you very much. That was really interesting. So we've had a couple of questions in from our viewers this evening, which I'm going to pose to both of you. So question one, so what additional support do you both feel the government could provide to support farmers with adopting farming practices which would enable better soil health and monitoring? So if I ask you, Phil, that question first of all.
Yeah, that's an interesting question. I think some clear messaging on soil from the government is really important. I think, if you look at the agriculture bill that's just gone through, in its first iteration, it was pretty low and looked like it wasn't really giving much attention to soil. But within that soil agriculture bill, there's, protecting, improving the quality of soil, and I think we need to really know what's the economic and environmental value of soil, and government needs to be really clear. Just a couple of other points I'd say as well is, let's have some incentives for good soil management as well. If there is incentives, then actually that is a real good way of getting farms to adopt it. And some of our environmental land management in the future, let's try and make sure that we get win-wins in the new environmental schemes. Strengthen advisory services, and probably the one thing I would say is when with specific reference to monitoring is, let's make sure that it's practical, streamlined, understandable for farmers, and it's uniform across all sectors. There's not different tests. So that would be my answer to that.
Yeah, well, I completely agree with Phil, and I hope there would be greater prominence of soil specifically in the new environment and agriculture bills. I think they're certainly a great step in the right direction, and the idea of public goods for public funds. It's important to remember, with this emphasis on environmental goods and services, farming is about producing food as well, and farmers need returns on that food production. Maybe they get a pretty small slice of the cake, so to allow them to do these additional things, it's important that their voice is heard firmly.
Yeah, definitely agree with that one. And the second question is, what impact, if any, do you feel the current pandemic and the highlight on climate change will have on influencing UK agriculture to adopt such practices, such as what's been discussed this evening?
Well, I think the fact was caught off guard so much by this pandemic, it is surely going to have a long-term impact. And it was not a question of if, it was a question of when there'd be a pandemic of this sort. So we've known a long time, but have failed to do anything about it. And the same applies for climate change. The writing's been on the wall, but it's not enough has been done. So this sort of thing will surely galvanize action and listen to the scientists. So I hope that it will have a serious beneficial long-term effect in that regard.
Yeah, I think if I come in there, I would say that if we can't see some of the valuable lessons that we've learned right in front of us, then we are in trouble. I don't think it can be business as usual. I think there's tremendous potential in the green economy, making that business. You know, trade and wealth have been important factors, but they've also led to quite a lot of exploitation of the planet. And I think, you know, especially around things like soil, you know, driving that intensity of production, whilst we needed to feed a population, we've got to get smarter at doing it. So I think there's got to be a willingness to change and a lot of partnership and developing win-wins. You know, wins for you know, profitable production, but wins for environment and for people on the planet. So I think there's some really valuable lessons, and we've got to grasp it and grasp it quick.
Cool. Thank you both for answering those questions, and thank you to our audience as well for providing those in. So, Guy, Phil, thank you ever so much for your time this evening and your wisdom and sharing best practices on the benefits of good soil health and both carbon sequestration. We hope that you found the content that we provided you this evening extremely interesting. I know I've certainly learned a thing or two this evening, so thank you very much to both. And as ever, we would welcome any feedback, so any event suggestions, any questions that you have on any other questions in relation to the content that's been discussed this evening, please do drop us an email on our Eagle Labs webpage. We do also have a session 3, a third soil event. For those that are interested, it's on Wednesday, the 3rd of June. And we will be able to share the Eventbrite link for that over the next few days. The third event is going to be on cover crops and the healthy soil effect. So keep your eyes peeled for that event coming up shortly. Thank you both again tonight, and I hope you've enjoyed. And yeah, we look forward to hopefully seeing you on the 3rd of June. So take care, everyone, and enjoy the rest of your evening.
Okay, thank you very much.
Thank you very much.
Thanks.
Bye now.